Welcome back. In this video, we're going to finish a problem that we started in class. So in this problem, we were going to use calculus to sketch the graph of f of x equals x squared minus 2x plus 4 all over x minus 2. We'd already gone through steps 1 through 4. We haven't sketched or plotted anything yet. We're not going to use a table of values. We never do that in calculus. We're getting the major features of the graph and gathering all that information so that we can sketch an accurate graph without plotting a million points. So we've already found the domain, the intercepts. We have figured out where the vertical asymptote is and the behavior on both sides of that vertical asymptote. So we know what it looks like. And now we are going to start differentiating. So in step 5, we're going to look for the intervals of increase and decrease, as well as the local extrema. We're going to find the x and y coordinates of those local extrema. All right, so we need the first derivative, so let's start differentiating. So f prime of x, using the quotient rule, is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Now we have to clean this up because we're going to have to factor it in order to find the zeros so we can get the critical numbers. So multiplying out, I get 2x squared minus 6x plus 4, and distributing that minus sign, I got negative x squared plus 2x minus 4. And the bottom is just still x minus 2 squared. And then we can see 2x squared minus x squared is just x squared, negative 6x plus 2x is negative 4x, and then 4 minus 4 is 0. So the numerator is x squared minus 4x. The denominator is still x minus 2 squared. All right, so let's factor. We pull out an x. And now we can see that our critical numbers are just x equals 0 and x equals 4. And you might wonder, what happened to x equals 2? Aren't the critical numbers supposed to be also, but the derivative doesn't exist? Well, that's why we found the domain in step 1, because we found that 2 is not in the domain, and so 2 can't be a critical number. So we don't include that number. But we're going to have to use it anyway when we do our sign diagram. So now we're going to do the sign diagram. We include the critical numbers on the number line and the number where our domain got broken up. We had to break up the domain into 2 intervals, the union of 2 intervals, and 2 is where that union came together. So now we're going to find the sign of f prime on these intervals, and it'll tell us the behavior of f on those intervals. So first of all, we knew f prime was 0 at 0 and at 4, and also we found, or we can tell, f prime doesn't exist at 2. So now to test the intervals, to see the sign of the derivative on those intervals, we pick a test point. So in the interval from negative infinity up to 0, I can choose negative 1. And notice that when I plug into my derivative, notice the denominator is x minus 2 squared. It's always positive. Doesn't matter what I plug in. So I just have to look at the numerator to determine the sign of the derivative. So if I plug in negative 1 into the numerator, I get a negative number times a negative number. So I get a positive number. Positive, the derivative is positive throughout that interval because it's a continuous function. All right, between 0 and 2, I can choose positive 1, plug that into the numerator of the first derivative, and I get a positive number times a negative number, so the derivative is negative everywhere in that interval. Now, between 2 and 4, plug in positive 1, I get a positive times a negative, so I get a negative first derivative on that entire interval. Then between 4 and positive infinity, I can just plug in 5. I get, in the numerator, the derivative, I get a positive number times a positive number. So the derivative is positive. So that tells us the behavior of f. So on the first interval, from negative infinity up to 0, it's an increasing function. Then it's decreasing, and then it's decreasing again, and then it's increasing. So we can write down our intervals. F is increasing on the interval from negative infinity to 0, and again from 4 to positive infinity. It's decreasing on the interval from 0 to 2, and again from 2 to 4. We can't include the number 2 because it's not in the domain. The function isn't doing anything at 2. All right. In fact, we found that was where the vertical asymptote occurred. We wrote that down earlier. So now we can write down the local extrema, but we have to find the y-coordinates. So we know where they occur, but we need to plug in those numbers to find out what they are, because we need both the x-coordinate and the y-coordinate in order to plot the points. So we know that 0 gave us a max, so we plug 0 into the function and get 4 over negative 2, which is negative 2. We could see that 4 is a minimum, so f of 4 turns out to be 12 over 2, or 6. So the local max is 0, negative 2, and the local min is 4, 6. So we circle those. All this information is going to be used when we sketch the graph. All right. Now we're moving on to step 6. Step 6 is to find the concavity of the function, the graph of the function. Find the intervals in which it's concave up and concave down, and any points of inflection. So we need the second derivative. So let's write down the first derivative. We had x squared minus 4x over x minus 2 squared. Differentiating this to get our second derivative, using the quotient rule, it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So the denominator is now x minus 2 to the 4th. Now we're going to have to clean this up so we can factor it and figure out where this thing is 0. So first of all, I notice I want to factor out any greatest common factor. I have something minus something else, and each of those terms is a product. So I look at the factors. Don't multiply these things out, because you're just making more work for yourself. If you multiply these things out, then you're going to end up having to factor in the end anyway. So let's just leave it alone and start factoring now. So look at both terms and look for a greatest common factor. And we can see that we have a 2x minus 4 and a 2 times x minus 2. So those are the same. 2 times x minus 2 is the same as 2x minus 4. That's our greatest common factor. So pull that out in front. So I'm pulling it out as 2 times x minus 2. Then in the first term, I'm just left with the x minus 2 squared. And the second term, I'm left with x squared minus 4x. Now, I can, my denominator is x minus 2 to the 4th. Now I can see there's a little bit of cancellation I can do. I have an x minus 2 in the numerator, and I have 4 of them in the denominator, so let's cancel one of them. And let's rewrite inside those brackets. I multiplied out the x minus 2 squared, and I distributed the minus sign in the x squared minus 4x. And my denominator is still x minus 2 to the 3rd. So now I can see x squared minus x squared is nothing, and negative 4x plus 4x is nothing. So I'm just left with a 2 times 4 in the numerator, and the x minus 2 to the 3rd in the denominator. So there's my second derivative totally simplified. And we can see that that's not going to be 0 anywhere. But it doesn't exist at x equals 2. So we can make a sign diagram and look at the sign of the second derivative on the left of 2 and on the right of 2. It doesn't exist at 2. So put a little star there. So plugging in something less than 2, like 0, I get a positive number over a negative number raised to the third power, which is a negative number. So I get a negative second derivative. And then for x greater than 2, just pick 3, and you get 8 over positive 1 to the third. So that's just 8, so it's a positive number. So we can tell from our sign diagram that f is going to be concave down, and then it switches to concave up. So our intervals of concavity, we can write down f is going to be concave down from negative infinity to 2, and then f is going to be concave up from 2 to infinity. But we do not have a point of inflection, no inflection point. And that's because we don't have a point at all at x equals 2. 2 is not in the domain. So it's not a critical number, it's not a point of inflection, but something's happening there. All right, so now we're set to graph. So let's sketch the graph of the function f of x equals x squared minus 2x plus 4 over x minus 2. So let's use all the information that we've gathered. So we draw our x and y axes, and we put in our asymptotes. We found a vertical asymptote. The line x equals 2 is a vertical asymptote. And we found a slant asymptote. The line y equals x is a slant asymptote. So we use those as guides when we sketch the graph. Now the points that we found, we had no x-intercepts. We had one y-intercept at 0, -2. And that turned out also to be a local max. Then the only other point we found was a local minimum at 4, 6. That was a local min. So now we're going to have to sketch the graph using the fact that we know it's increasing from negative infinity up to 0, and then decreasing again from 0 to 2, and it's concave down the entire time. So we're approaching these two asymptotes, and we know that after x equals 2, that the graph is decreasing from 2 to x equals 4, and then it's increasing after 4, from 4 to infinity. And it has a local min at x equals 4, and it's concave up that entire time. So now we can sketch the two pieces. The piece on the left has to look like this, and then the piece on the right, where it's concave up, has to look like that. And that's it. We've used all the information. We've sketched an accurate graph. We've never made a table of values. We've only made a couple of sign diagrams and calculated limits and derivatives. All right. I'll see you in the next video.